note, this specific one, I don't remember, I want to say you've seen chromic acid before, right? Okay, so you've used this in other chapters to do some oxidations. I don't remember exactly what this will oxidate, but this one down here, they're specifically showing you, you can have an alcohol, you can have an ether, it's not going to touch those. It's just going to oxidate your aldehyde. Yeah. Also, vanillin smells exactly like you think it would, exactly as good as you think it does. And I used to use it as like my scented candle because I taught in a very small school and they used the same cats for anatomy and physiology first semester and second semester. So by second semester, so I'd get a little hot plate and turn it on very, very low. I put a bunch of vanillin in there that I found in the stockroom, and then like every morning I'd just sort of fill the crucible back up with water and keep it on warm, and it was much better. Yeah, just, you know.
On the previous slide, what is like the degree sign on the silver?
The what?
What is that little, like the circle?
Oh. Oh, I hate that. So that is, they put a 0 up where you'd put a charge to show you like, this is silver metal. But like, I don't know, put a parentheses S, put a like down arrow, because metals fall out of solution and gases rise up out of solution, so chemists are inherently lazy and sometimes parentheses in a letter are too much for us to write. But like, that is awful. Can I? Oh, yeah, because that's extended. That's what my mouse always does. Would it be useful if I like cropped that out of this so you guys don't have to worry about that in your post-lecture slides? Or is this, are we okay?
I think it's just there to show like that something's reduced because whenever one thing's oxidized, another thing has to be reduced.
Yeah,
So
I
if
just,
that's what's reduced.
like, I don't know, write all of the oxidation numbers or something, or none of them, because yeah, no, that looks like a degree symbol and that's dumb. That's really funny. I'm sure I've seen it before, but I don't like it. Oxidation of aldehydes. So Tollens reagent is another form of silver 1. And if you notice back, yeah, this is how you form Tollens reagent. So if you have ever done the mirror, the silver mirror experiment, where you like you do an experiment and just like you roll it around and you get to coat the inside of some sort of glassware with just like a mirror finish. We did that in high school and we got to bring our own glassware, so everybody went to Hobby Lobby right before and got like weird shapes and stuff. It was very fun. I still have it with a cork in there because I didn't actually wash it out afterwards. So Tollens reagent, this is how you make Tollens reagent. It's another form of silver 1. So this is, instead of using straight up silver 1 oxide, you're going to dissolve that in aqueous ammonia, so you basically end up with this guy. They say silver 1 oxide, but this to me looks like you're dissolving silver nitrate in ammonia so that you don't have to deal with silver oxide at all. I don't know if the slides are wrong or if they're just, this is the reaction that they're interested in showing you, but you actually do dissolve that. Oh. Okay, so maybe there's a chance that the silver oxide just immediately oxidizes one of these into that. I don't really know. But anyway, just ignore that part. this part, this is a tolerance reagent. That's how you make a tolerance reagent. This is a tolerance reagent. And same thing, when you add it to an aldehyde, it's going to oxidize to a carboxylic anion. And silver one is reduced to metallic silver. So if you like put everything into the bottom of a flask really gently, and then instead of really mixing it, you just sort of roll it back and forth and like, tip it so it covers everything, then you get a nice silver mirror finish on the inside of whatever glassware you wanted. And I don't know, it's kind of nice. Aldehydes can be oxidized to carboxylic acid by molecular oxygen and by hydrogen peroxide. With oxygen, that's going to be a radical chain reaction, so I'm not going to make you write the mechanism for this, but like radical, has anybody, like, I don't know, have you ever seen radical mechanisms or radical, okay, yeah, so it's when you do like half an arrow and stuff, so it's a thing. A bunch of these we're not going to have to know mechanisms, only some of them. Let's see. Oh, and liquid aldehydes are so sensitive to air that they must be stored under nitrogen gas. Yeah, so maybe Schlinkline glove box. I don't really know. I want to say it's probably more of a situation where, because like metals are finicky. Like when they say you need to store those under nitrogen or argon, like they need it, and that metal will die. And metals people work with very little of their stuff because first they have to be organic chemists and like make very specific ligands, and then they have to put them on metals, and half the time they're expensive metals and all sorts of stuff. I am not entirely sure, but I would suspect liquid aldehydes are probably somewhere in the realm of like put it under a flow of nitrogen when you open it and kind of try and store it under nitrogen, but not entirely sure. At least that's what I do with most things, and I mean with a liquid, you don't want to evaporate, but I don't know. I do that with solids. Pinnick oxidation. We have a mechanism for this one. This is an inexpensive method to oxidize an aldehyde to a carboxylic acid. So if we go back here, we're using straight up silver or chromium, which, I mean, those have value, right? So this is a much cheaper way to do it. I mean, if you're doing like micro scale organic chemistry, or if you're doing, a couple grams in the lab because you're trying to make something, who cares, right? But if you're trying to turn an aldehyde into a carboxylic acid on a scale of like industrial giant things because you're making a drug, it, if we didn't live here, might really help drug prices stay lower because by doing something like this, because this helps manufacturing prices stay lower. But because we live here, this helps manufacturing prices stay lower, but not drug prices, because we live in a dystopia. It's fine. No, I just have a lot against the problems that cause that. And there's no easy fix, but I like to complain. So this is a selective procedure that will not oxidize alcohols, which is good to know because chromic acid, I want to say chromic acid will oxidize alcohols. Is that what it oxidizes? You've seen chromic acid before. I want to say it'll oxidize alcohols. I don't know if there's anything else it'll oxidize.
Yeah, I was gonna ask, so since in the vanillin one, since it was like on a benzene, is that why it wouldn't oxidize the alcohol?
Oh, no. So this guy is... Wait, did you do silver
No,
one?
sorry, I didn't, I thought. that
Okay,
was
yeah,
also
sorry.
chromic,
This
but-
is, yeah. So that's why I pointed that out like right after. I may have like said those two similar, like too close together. But yeah, I wanted to point out specifically, they put a bunch of other stuff on this one to show you that you can use silver 1 oxide or later the Tollens reagent to oxidize an aldehyde without messing with the alcohols. I think ethers, can you even oxidize ethers? Does anyone remember? I want to say ethers are pretty well just fine, in which case,
I don't think it's possible, right? Because they have to be bonded to two things, and then they have two lone pairs of electrons.
yeah, and I'm trying to figure out, there's not like a leaving group.
We were a little behind when we got to ether, so we didn't exactly.
Totally fair. We're gonna be a little bit behind when we get to a lot of things too. In fact, I might like very much change the benzene slides to like hit some of the important points in more the style that Smithrid does. Not that I can really see his style because he doesn't use slides, but from his syllabus, I can get an idea of which things he does. So, Pinnick oxidation. More expensive, less expensive, more inexpensive than the other two. And less expensive than the other two, and is selective, will not oxidize. If you really, really wanted to use chromic acid and you had an alcohol you have like a compound that has an aldehyde on it and an alcohol on it, and you only have chromic acid, and it's the only way you could ever oxidize anything because, I don't know, come up with a reason. What could you do to protect the alcohol? Use a protecting group. Okay, so like, what protecting group did we just go over?
Cyclic acid.
Yeah, you could use acetal. You could make a little cyclic acetal and just boop, make it a little 5-membered ring, and then when you're done, get rid of that. Because I'm pretty sure, I think you could do that. I'm pretty sure, because this reaction doesn't seem to need to be in water. I'm pretty sure you could do that anhydrous, and yeah, you could totally do that anhydrous. Anhydrously, is that a word? Anhydrously? You could do this in an anhydrous manner. So yeah, with the Tollens reagent, or with the silver reagent, they actually have like water and aqueous acid in there, so we couldn't protect with the same way, the same way, because that's how you take off the protecting group, but we don't have to because it's selective, right? Okay. Sorry, side notes, lots of side notes. Let's start over here with, which is not right. Then it'll stop challenging me to pretend I'm tall. H2PO minus. Handwriting is weirdly legible today. Okay, so first step is that we end up with chlorous acid. This uses, it says it uses sodium chlorite with a phosphate buffer. So basically, we start with one hydrogen already gone from each of these. Well, this is deprotonated, and this is once deprotonated already because we started with the anions, and a phosphate buffer. So those react, we get this, chlorous acid, and that's what we're gonna use. So, let's do, can chromic acid, oxidate like a double bond or something like that too? I don't know. Like a multiple bond, I don't know. I feel like there's some way to oxidate a multiple bond where you just, and either one or both of them get OH groups. So we don't actually know. But,
It's a hydrogen reaction.
I think it's osmium.
oh, okay, yeah. That would be why I don't remember that, because like, it's osmium.
So we're definitely gonna have to reach it.
You don't have to remember a ton from first semester. If there are things that I want you to know from first semester, I'm going to, which I think there are, I'm gonna go through and like kind of make a list of like, here are the things that are fair game. Know these things, just a couple basic like transformations so that I can do multi-step syntheses or something like that. Your homework definitely has stuff from first semester, and the reaction, what is it, reaction roadway, reaction map, whatever that is. You know what I'm talking about, that your book has? Yeah, that thing, I don't know what it's called. That kind of is supposed to work like a flowchart, so that should be, it may or may not be useful as a cheat sheet for getting through some of those homework problems.